So now that we have all of the background, let's take a look at sampling with means. So what I want to be able to do is to answer questions about what I can expect to find in a sample of a certain size, and certain size is important, based on the characteristics of the population I'm taking the sample from. So let's say I have this population and I know the mean of the population. Then no matter the size of the sample, then the mean of my sample, that's what this one means, the mean of my sample is going to be equal to the mean of the population. So if I give you a mean for the population, you're going to use that as the mean of your sample as well. In terms of the standard deviation of our sample, and again that X bar is representing sample, so the standard deviation of my sample is going to be equal to the standard deviation of the population. So this is the SD of the population, and that's why we're using Greek symbols, divided by the square root of the sample size. Remember, n is the sample size, so divided by the square root of n. So that means, assuming our conditions are met, which we just talked about, we will be able to use what we know about a normal model, Z-scores, empirical rule, probabilities, etc., in inference with means, and our normal model is going to be mu, comma, sigma divided by the square root of n. Now this probably doesn't make sense yet, and that's okay, because it really makes so much more sense when we look at an example. So here's the steps we're going to follow. The first thing we're going to do, and again this is for means, so things will change when we look at proportions, but for means I want to first check the conditions, and these are the same conditions that I had listed before. Notice I'm using large enough here instead of success fail, because large enough goes with means. Then I'm going to perform the calculations, which means I'm going to find a z-score, and I'm going to use that z-score to find a probability, or I'm going to possibly do the empirical rule. And so maybe all of my calculations will just be to find the standard deviation, which is sigma divided by square root of n. So it really depends, and I'm going to give you some of each type of question. Then we're going to state our conclusion in the context of the question. So let's take a look at our first example, sampling with means. It says, at birth, babies average 7.8 pounds. So notice I've underlined average, which is not normally going to be the case, but I underlined it for you so that you knew, because I'm dealing with average, this is a means question. That's how I know that I'm using means. And then it gives me my mean of 7.8 pounds. So 7.8 pounds is what I will expect, whether that's the population of babies or a sample of 10 or 20 or 30 or 50 babies. I would still expect the average weight of a baby to be 7.8, either way. So remember when I said m sub x bar is equal, or sorry, mu sub x bar is equal to mu, that's what I mean. The mu is 7.8, but that means my mean of my sample is also 7.8. Then it gives me my standard deviation of 21 pounds. I'm sorry, wow, that would be crazy. 2.1 pounds, and 2.1 pounds is my sigma. But remember, sigma is the standard deviation of my population. The standard deviation of my sample is going to be sigma divided by radical n, and n is how many babies we're dealing with. So just to kind of keep everything straight, these are the values that I'm looking at. Now, the question I'm trying to answer is that unusually low? Now, before I can get started with all of these great things, I need to look at the conditions. I want to check to see that I can use this sample to make a decision about the population of all babies. So here's my conditions, random. Now keep in mind, when I'm checking my conditions, notice I'm not saying random, yes, 10%, yes. So when you check a condition, I will be looking at, did you explain it, and did you explain it in a way that I know that you understand what that condition means? So the first condition is random, and what I'm looking for is, do we have a random sample? And yes, 34 babies were randomly selected. So I knew that because it told me in the question. 10% is talking about the 34 babies. So they're saying 34 babies is your sample. Is 34 babies less than 10% of the population? And the population is babies. So we're comparing the sample to the rest of the world of babies. And so yes, 34 is less than 10% of all babies born. Independence is talking about whatever you're measuring about that sample, and in this case I'm measuring how heavy these babies are, is that characteristic independent sample by sample or baby by baby? And in this case, yes, I can say the birth weight of a baby is independent of another baby's weight. And why do I know that? Because I'm sampling these babies randomly. So if I took, babies that were siblings, then no, it's probably not going to be independent because same mother, same father, same home environment, etc. But because they're randomly selected, their birth weights are independent. And then large enough sample, we're looking for n is greater than or equal to 30 or a nearly normal distribution. And yes, n is greater than 30, so we can assume the sample is large enough, but obviously weight is a normally distributed variable anyway. So once I've checked the conditions, then I say this: because the conditions are met, I can use a normal model. Well, what's the model that I'm using? I'm using the information from my sample. So I'm using the mean of my sample, which is 7.8, and I'm using the standard deviation of my sample. So I'm not using 2.1, I'm using 2.1 divided by radical 34, and notice I've written that here again, and then I went ahead and computed this out to 2 places. So just keep in mind that the instruction should tell you how many places to go to. That's the first thing, is check the conditions. Then we're going to draw a picture. And drawing a picture, again, most of the time is optional unless it's the, write the empirical rule values. But here it would be optional, but what I'm looking for is I'm expecting 7.8, and I'm trying to find the probability that I have a mean birth weight of 7.2 pounds or less. So where did I pull that or less from? Well, I'm asking, is this unusually low? And so what we look at is, what's the probability of the value that I found or more extreme? So in this case, more extreme would mean that the mean birth weight is even less than 7.2. So keep in mind that this is going to be a less than or equal to when I start looking at probabilities. So now that I have my normal model that I'm using, I'm going to perform the calculations to find a z-score. And so remember, my z-score is the observed y-bar or x-bar, whichever way you do it, minus my expected. And my expected, remember, was the mean, and the standard deviation was the standard deviation divided by radical n. Now I already determined this value on my last slide of 0.36, and I already know that this value is 7.8 because that was given to me. So notice all I'm going to do is take my observed minus my expected divided by the standard deviation, and if I showed this work on the last page, I don't have to show the work again, and I get a z-score of negative 1.667, then I'm going to go into StatCrunch and I'm going to plug that value in. And you might be asking, can I use that cheat method that you just reminded me of? Well, if I'm giving you a question like this, you have to find the z-score. So whether you use that cheat method to check your work or not is up to you, but I will be looking for this. Can you determine it from StatCrunch using your z-score? And then this is the answer that I came up with, 0.0478 rounded correctly. So again, note the way my probability is written. Probability of y-bar is less than 7.2, is equal to the probability that z is less than negative 1.667 is equal to 0.0478. Then I need to answer the question, is this unusually low? So it says according to the normal model, only about 4.78% of samples of 34 babies are expected to have a mean birth weight below 7.2 pounds, and that's assuming that this is correct. If it's true that babies at birth average 7.8 pounds, I'm only going to find a sample with that low of a birth weight 4.78% of the time. And so it does appear, because that doesn't happen very often, that the babies near the factory appear to have an unusually low mean birth weight. So let's look at another example. This one I'm asking you to use the empirical rule, which means I'm not going to find a z-score on this one. This one says the speed of cars on a highway have a mean of 52 miles per hour and a standard deviation of 6. So remember, that means the population has a normal model of 52,6. But the sample has a normal model of 52, what? I'm going to take 6 divided by the square root of the sample size, which is 50. So I'll show that work in a little bit, but I just want you to be clear about which is which. So the first thing I would do here is, of course, check the conditions. So same conditions as before. Random, 50 cars were randomly selected. We were told that they were. 10%, 50 is less than 10% of the cars on the highway. So again, less than 10% of the population. The population is cars on the highway. Independence, because we're randomly selecting these cars, the car speeds are independent. So because they're randomly selected, we don't have two yahoos driving next to each other and trying to race each other. Large enough condition, n is greater than 30, so we can assume the sample is large enough. So now what? Now I'm going to do the calculations. And again, last time I looked at the picture first and then the calculations. This time I'm doing it out of order, since my answer is the picture of the empirical rule. So my mean of my sample is 52, which we already talked about up here. The standard deviation of my sample is the standard deviation divided by radical n, which is 0.849. So notice I write my sentence that says, because the conditions are met, I will use a normal model, n 52, 0.849. So now what do? Now I'm actually going to draw the picture. So typically, if you have a question like this, you will just be filling in the blanks for these values down here. But again, where did those values come from? I started with 52 in the middle. I used that 0.849 to add, to add, to add, to subtract, to subtract, to subtract. And if you watched the previous video on the reminder of the normal model, I showed you how to do that in StatCrunch using a mean of 52 and a standard deviation of 0.849 and clicking on this button. And again, I want you to notice though that this is rounding my values to 2 decimal places, and so if you're doing an assessment type of question, make sure that those values are rounded to the same number of values that I've asked for in the question. And then my conclusion in context is essentially saying in words what I can look at the empirical rule and say, which is 68% of the samples of 50 cars have speeds between 51.5 and 52.85. 95%, that's within 2 standard deviations, has speeds between 50.3 miles per hour and 53.7, and 99.7 between 49.45 and 54.55. So here's another example, and this is a little bit different and it is a little bit harder, and I definitely gave you one of these on your homework, so pay attention. Here I am sampling with means, but I'm given data. So what does that mean? That means in all of the other questions, I told you what the mean was and I told you what the standard deviation was. Here, I'm not telling you anything. I'm saying, hey, look, here's some raw data. What are you going to do about it? So what I'm looking for here, and again, the question, in case you have been listening to me talk and haven't read the question, is that this is the table for score distribution for an AP statistics exam. There were 61 students, so of course n is 61, and were considered they're not a random sample, but we considered his students to be typical of the national students. What's the probability that his students will achieve an average score of at least 3? So I'm trying to find the probability that x is greater than or equal to 3. Well, how am I going to do that when I don't know the mean and I don't know the standard deviation? Well, luckily, I know StatCrunch, and StatCrunch can help me find the mean and standard deviation I need. So let's take a look at that together. So all I have here is data, and I don't have any of my summary statistics. So I'm going to go ahead and enter, because it's not going to be there for me already. Maybe I'll get lucky, but in this case it's not. So I'm going to put 5, 4, 3, 2, 1, and I'm going to put the percent of students, and I'm going to put 0.133 instead of 13.3, and 0.219, and 0.251, and 0.187, and 0.210. So that's all of the same values. I just wrote them as decimals instead. And what I want to do is I want to find the mean and standard deviation of this information. So I'm going to go to Stat, Calculators, Custom, and because I have scores and percentages, a weighted column, then I can use that. And notice what it gives me is a mean of 2.878 and a standard deviation of 1.3278, etc. So that is what I would need in order to then use that mean and standard deviation throughout the problem. But be careful. So looking at the conditions, we already know that the teacher said, yes, this is typical of national students, so I don't have to check anything else. But be careful on the sample, because when I found my mean, it was 2.878. When I found my standard deviation, it was 1.3278. But remember, I can't just use 1.3278 because I have to look at that in terms of a sample of 61 students. So notice I have divided that by radical n, which is radical 61. This is the model that I'm using. So I see a lot of people make that mistake of trying to use the 1.3278, and of course that's going to give you a very wrong answer. So again, what would I do next? I would find a z-score. My observed value is 3. That's what I'm testing. I'm saying 3 or more, so at least 3 means 3 or more. So I found my z-score, which is 3 minus my mean of 2.878 found in StatCrunch, divided by that standard deviation, not from StatCrunch, but from StatCrunch, and then divided by radical 61 to give me this z-score. And then I'm going to write my correct probability notation and say the probability that y bar is greater than or equal to 3 is equal to the probability that z is greater than or equal to 0.7176. And here is my solution, again from StatCrunch. So I'm showing you the output, normal calculator, mean of 0, standard deviation of 1. I entered in my z-score, I got out my probability.